Let me introduce Professor Portenko, who is well-known specialist in a series of diffusion processes. And it's my great pleasure that Professor Portenko agreed to deliver this beautiful course. Paul Ivanovich, please.
Thank you. Good morning. I have chosen for my lessons this semester a course by the title of Diffusion Processes. I hope you, my listener, have already had an opportunity to look through the program of my course, and I'm going to keep on program and but without any fanaticity. When speaking about the very beginning of the theory of diffusion processes, one should mention an English botanist by the name of Roger Brown, who discovered some phenomenon that can be called Brownian motion. Almost 200 years ago, he put a grain of flower pollen, and he took a grain of flower pollen and put it into a liquid and started observing its behavior through a microscope. To his astonishment, this particle turned out to be incessantly moving in a chaotic, unpredictable manner. Modern physics explains this motion as the result of collisions between this particle and molecules of the liquid. And the first mathematical model for describing such a motion was constructed by Norbert Miller. About 100 years ago. He considered it, that motion as a Gaussian random process of certain Gaussian random process, and constructed its distribution on the space of continuous functions, real valued continuous functions that are given on some interval of real life. The next step in the development of this theory of diffusion processes, is connected with the name by Andrei Kolmogorov. He published at the beginning of the 1930s. He published an article that is called. It was published in German, and its title was über die über die analytische Methode in der Wahrscheinlichkeitsrechnung. He singled out a class of Markov processes that came to be called later diffusion processes. The main idea of Kolmogorov was as follows. Such a particle takes part in two kinds of motion. The first one is a macroscopic motion. There might be some streams in the liquid or beneath in the gas. And so this particle takes part in a macroscopic motion, and this motion is characterized by fixed velocity. Vector field of velocities. You can see that diffusion in the Euclidean space. This is notation for d-dimensional Euclidean space. And ASX is a vector field. That is, this function is RD value and means, and this is the macroscopic velocity of our particle at the point x of space at time s. This is a macroscopic characteristic, and the second kind of motion is microscopic motion, and it is characterized by the operator field BSX. And I will give exact definition by tomorrow, some of later. But this is some characteristic of the microscopic motion. So the Brownian motion in some liquid maybe it may be river or gas. The motion of such a particle consists of two kinds of two parts. Macroscopic motion that is determined by this vector field and the microscopic motion that is determined by this operator. Tomorrow, that publication proved the following result. Let us consider some function phi of x defined on our Euclidean space and consider expectation of phi of x of t, conditional expectation if we know that our particle starts at time s from the point x in Rd. Denote this function by u s x t to make a phi. Where s is less than t, x is the point from Rd. Suppose that this function is such that this function is twice differentiable with respect to this function. And we proved if the process is a diffusion one, and this function is such that that function is such that this function is twice continuously differentiable with respect to x. We proved that this function is a solution to the following partial differential equation: du ds equals a s x the derivative of this function plus 1/2 trace ds x. The second derivative of this function u with respect to x I'm sorry, here I would like to correct. This sum is equal to 0 if s is belongs to this interval. X is a point from Rd. And the following initial not initial ut minus x e phi equals phi of x for all x from Rd. This is not initial, but on the contrary, S is in the interval 0 t, yes, t, and well, this is the limit of our function u as x t, t as x goes to t. Okay, so it was a very strong result. It showed that the theory of diffusion processes in the sense of Kolmogorov are connected with the partial differential equations of the second order, and this equation is of parabolic type because b as x, according to its definition, this is, I would like to recall, this is some local characteristics of the microscopic motion of our part. Okay, this form is non-negative definite. So this is a partial differential, the second order partial differential equation of parabolic type. So the next development of the theory of diffusion processes was connected with this equation. The starting point of my course lesson will be this Kolmogorov's theory of diffusion processes. I would like to formulate its. I would like to. I'm going to formulate exact definition of the diffusion process according to Kolmogorov, and we derived this equation. This equation is called the Kolmogorov backward equation. So this equation is shown in that publication that the corresponding is fact that some other equation is connected with it, and that equation was known in physics as the Fokker-Planck equation. The aim of my course is to teach my listener for constructing some new classes of diffusion processes. I especially will pay your attention to the situation when the these functions are not regular. What does it mean? If this function, for example, if function a as X is not regular, it means that some, for example, A as X is not locally bounded. It means that at some times, at some points of X, there may be some vertices in that liquid or gas. It is natural that in that case we cannot expect that the corresponding process is diffusion in the sense of Kolmogorov. So we should extend the notion of diffusion process, and I hope we will construct some examples of diffusion with irregular coefficients, and we'll try to give some interpretation of them. I start with resolving some notions of the theory of Markov. And I have already said my Tomahawk notion of diffusion. This is a Markov process, and I would like to recall I suppose that my measurements are excellent. The Kolmogorov actions. So if we have some measurable space, X, the sigma algebra of subsets of X, subsets of X. And if we speak about the random element in X, C is random element. Next, that there is some probability space in sigma algebra F. The elements of F are called events. So if some A is F, we can speak about the probability of A. So if we have random element with X, it means that C is a function of a function defined on this space, a function of omega. And this is such a function that the set of all omega for which C of omega is a point in the measurable set gamma. This set is an event this that it belongs to F. We can say about its probability of this event. As a rule, we will omit this argument, but we will keep it in our mind. Okay, if I have a random process, if I have a random process in this space, so I have a family of random elements. Family subset of T capital is a subset of the real line. So for any fixed T, x of T is a random element, means that the set of I like to write down it further. X of T belongs to gamma, means set of all omega for which x T omega belongs to gamma. This is the short notation for this event. This event is an event. This set is an event. Means it belongs to that. Okay? For any T, for any T from T, and for any gamma from B. And now suppose that we have some random process in this space, and the question arises how to describe evolution of this process, how to describe the evolution of this process in probabilistic manner. It's clear that the best description will be of the following form. If we can calculate the following probability, x of T belongs to gamma, conditional probability, given, I would like to write down this M handwriting MS, and explain what is it. Suppose that we have a family of sub-sigma algebras of sigma algebra F such that NS is a part of MT for all S less than T. S and T must be from T capital. Suppose that we have some family of sub-sigma algebras such that satisfies the following condition. MS is a part of MT for any S less than T. Then we call this family of sigma algebra a history. This is a history. Events, some this sigma algebra consists of some events from this sigma algebra, okay? And this includes true if S is less a history or a filtration. A filtration. If we have some process X of T, it is not difficult to construct its history. You know, by N and writing T, the minimal sigma algebra that is generated by the following events. XS is a point from gamma for all S less than T from T capital, and gamma belongs to the minimal sigma algebra that is generated by these events for any S that are less or equal to less than T or equal to T, and for all gamma from T. Okay? This sigma algebra is the set of all events connected with our process up to the instant of time T. Okay?
So, gamma, isn't gamma supposed to be from F?
No,
From
from B. From B. We consider our process in the space XB. X of T, X of S takes its value in the space X. And gamma is the measurable set. Okay? So it is evident that this is a history or a filtration, and it is called the history of the process X of T, its own history. If we have that for some sigma algebra M of T, the sigma algebra N of T, N of T consists, is contained in MT for all T, then we say that our process X of T is adapted to this history. Its own history. And in the history, then our process is adapted to this history. Okay? Now, I would like to assert that the best description from probabilistic points of view, description of our group is if we know these probabilities for any S less than T and for any gamma B, this is some prediction of the behavior of our process at the instant of time of T, given that the complete information about the events in the past up to the instant of time S, including S. So if we can calculate these probabilities for different S, for any pair of S and T, and for any gamma, we will have some prediction. We will calculate some prediction for our process in the future. Okay, but how calculate? How these probabilities can be calculated? It is very difficult to Kolmogorov single out the class of processes for which this prediction coincides almost surely with the following one. The probability of the same event given the following sigma algebra. X of S belongs to gamma belongs to B. This set of all events is a sigma algebra. Yes, if gamma we consider these events for all gamma from the sigma algebra B, we have this set forms a sigma algebra. So you see, von Horn suppose that our process is such that this prediction of the behavior of our process in the future, this prediction that takes into account all the events up to the instant of time s. Okay? This prediction is as precise as that one that takes into account only the state of our process at the last instant of time, at the instant of time s. So all the events that happened before this time do not influence on this prediction.
Nikolai Ivanovich,
Yeah.
probably gamma in the conditional probabilities are different in condition and in event. Xt belongs to gamma with tilde. So it's another gamma.
Oh, yes, yes. Oh, thank you, thank you. Thank you. Right down here. Yes. Lambda. Thank you. Okay.
And I have one more question. So we assume that there exists a pair, a process and a filtration M.
Yes, this process, Kolmogorov called the process that satisfies this condition stochastically determined. Stochastically determined. Now, this property is called the Markov property. If our process possesses this property for all s less than t for all gamma, our such a process is called a Markov process. Called a Markov process with respect to history mt. We suppose that our process is adapted to that location, to that history. So mt is a part of mt. Okay? As a rule, one write down here n s. But there are very simple examples when the process is a Markov possesses a Markov property with respect to a history that is richer than its own history. Okay. And now, if our process is a Markovian one, then let us look at this probability. This probability is a conditional probability of some events given the position, the location of our process at the instant of time s. Okay? The last time. It is known that if you have some expectation of of something given a random element, then this is a function of some function of C. And this function is determined not uniquely. So this probability can be written as this P is different from this one. This is a measure, this is a function. It depends on S, T, and X. Okay, so I can write down here S, X, T, gamma, and this function, there exists some function with its values in the interval 0, 1. This is the probability, yes, the conditional probability. So its values are interval, and it is such, it must be B measurable in this argument, okay? And it is such that if I substitute X by X of S, so I will assume the equality, this probability is equal to value of this function if I substitute X of S instead of X. And
I have a question.
yeah,
What is the dependency on X in this probability? It's the starting point for
no, it's
the X which is in the function. Where is it? This probability.
I have used the following result.
Mhm.
If I have C, an element in X, yes, and I calculate the expectation of some random variable given C. I have just used the following assumption. There exists a function f of x that is B measurable and takes its values in the space. If this is a random variable, that this function takes its values in real life, okay? Real life, and it is defined on X and is B measurable, okay? And this is the result of substitution into this function of this random element, and this equality is almost sure. The expectation of something given random element is a function of this element.
Maybe the question was that we will denote these conditional probability with respect to sigma algebra generated by x of s, just x of, you may write x of s here. So this is a shortcut for this for this conditional probability.
Yes, this function is f. Here. Okay. You see, we have this is expectation of indicator given x of x. Okay.
This thing I understand, but where I see that this b, the last b, the shortcut, it depends on s, t, and gamma. And where is the dependence on x? What is it?
Of x, this function. This function is.
Oh, you mean by the x in the last one? You mean the process itself?
Yes. Yes.
No, I understand. Thank you.
Okay. And moreover, there are other assumptions that I am going to use now. I mean the existence of regular conditional probability. If we have some the same situation at given C is element in X, I assume that in the nice spaces there exists such a function maybe there exists such a function you see it is evident that if we have that if we have some hammer n like that in this space and we consider as x of s t hammer n, then it tends to p s x of s t gamma as n goes to infinity almost surely. And if we have another sequence of subset of x, so we have the same property, but the what it takes place almost surely And so the question arises, if there exists such a function as x t gamma that has this property, for all x and for all gamma n. And it must be such that if I substitute xs instead of x, we receive this conditional probability. The general fact is as follows. One can choose such a version of this function. This function is determined not uniquely. So one can choose such a version of this function that possesses the following properties. For fixed s and gamma, this function as a function of this argument is measurable.
So this convergence due to the continuity of conditional probability.
Yes, yes, yes.
And
But
now we're considering just such functions with such convergence, and we want to construct our probability.
yes,
using
yes. I would like to choose to choose such a version of this function that satisfies the following condition. The first one, it is measurable, but and the second one, for fixed s less than t and x from x, it is a probability measure on B. And because it is the version of this function, so must be fulfilled the following property. This function is such that if I put x of s instead of x into it, I receive this probability, this conditional probability, x of t belongs to gamma, given x of s. This is short notation for this probability. I write down here x of s instead of sigma algebra that is generated by this random element. Okay, so such a version of our function exists according to the general theorem on the existing regular conditional probability. You can find this theorem in many monographs about monographs on probability theory. Okay, and now I would like to draw your attention to the following circumstance. Consider three instants of time as tau t. It is, or maybe, I'm sorry, I would like to make one remark. If we have regular version of this function, then the following equality is true. If for any bounded measurable function, x, for any bounded measurable function f defined on x capital, bounded measurable, this expectation given x s can be calculated as the integral over x f of y p s x t dy. In the situation when there exists regular conditional probability. So you see, according to this property, it is the probability measure, so I can consider the integrals of measurable functions. Yes, so this integral is well defined. And and I must write down here x equals x of x. And this is almost surely. The equality is true almost surely. If I put here x of x instead of x. Okay. And now if we have three instants of time, I can write down p s x of s t gamma is equal to expectation of e gamma of x of t given the history up to the instant of time, instant of time s, okay, according to this equality. Yes. And it can be rewritten as follows. Expectation E gamma of expectations E gamma over x of t given x of t given m tau given mx. Because tau is greater than s. So this sigma algebra is a part of this one. Okay? And now this term can be written as this can be written as p tau x of tau t gamma. Okay? So this is p tau x of t gamma, and I calculate the conditional expectation given m s. And now I have this situation. You see, this is a function of x of tau, and I can calculate this expectation as I can write down this expectation as the integral. I would like to write down here. The integral over x. You see, f of y, f of y, p tau y t dy with respect to psx of st dy.
T gamma.
Oh, excuse me, t gamma. Yes, yes. I'm sorry. Yes. P t y t gamma, and we integrate this function with respect to the measure psx of psx of x tau dy. So we have the following equality. We have the following equality. This probability coincides almost surely with this one, according to the property of regular conditional probability. This is a probability measure with respect to this argument. Yes, so I can integrate some functions with respect to this measure, and this function is be measurable as the function of the argument y, so it can be integrated. Well, this integral is well defined. Such equality And the question arises, is it true or not if I write down this equality not for x of s and mean that this equality is almost surely fulfilled? Is it true or not that we can write down the following equality? Y cubed gamma E s x tau dy. For all x, is it true or not that this equality is fulfilled for all s less than t, all x from x capital N, from all gamma from the sigma algebra B? You see, if I know that it is true if I put here x of s instead of x, I have this equality being true if I put x of s instead of x, and this equality fulfills almost surely. But I would like to write down and ask, is it true or not that there exists such a version of our regular diffusion probability? And this is a theorem that was proved by V. Kuznetsov. Published in 1980, the paper which is called Henry Markov Loses in a Barelian space possesses transition probability. A transition probability. This is a publication in the Moscow journal, Theory of Probability and Applications. And according to this theorem, if the space X is not bad, not very bad, then there exists such a version of conditional, of regular conditional probability that this equality is true for all s less than t, for all x in x capital and for all gamma in the sigma algebra. So I will now suppose that our version of that function satisfies this condition. tau y t gamma e x tau dy. This equality is fulfilled for all s less than t than tau, that is less than t, for all x and x, and for all gamma and t. We will consider our processes in a Euclidean space, so it is a Borelian space. So for our process, such a function, if our process is a Markov one, so such a function always exists. My time is over.
Depends. You want an hour or an hour and a half?
An hour and a half.
We have, I think, like 20 minutes.
20? Oh, okay. This is the definition of transition probability, and this is the definition of a Markov probability. That transition probability is such that if you put substitute x of s instead of x, we give this probability, and consequently this one. And we have already said that this probability is the best prediction from the point of probabilistic properties of our system. It is the best prediction. So we have for that prediction the following function. This is this the best probability, the best prediction coincides with this function if I put x of s instead of x. So our attention must concentrate on these functions. So we have some equation for this function. This equation is called Kolmogorov-Chapman equation. Kolmogorov-Chapman equation. Kolmogorov-Chapman equation. So in this equation are any solution of this equation, but that satisfies this equation. You see, we can write down this equation only under these two conditions, because you have to integrate with respect to this, it must be measured, and we have the integrand must be the measurable function of y according to this. So only under these conditions we may write down this equation. And I would like to consider some examples of solutions of that. We will call the process a Markov process. As a rule, I will consider some processes that are defined for all the instances of time, or maybe some interval. Or if I have a Markov process, as a rule, I will consider them in a Euclidean space of the dimension B into the sigma algebra of Borelian subsets of RD, and we call this process homogeneous if the following: if its transition probability has the following property: S x S plus T comma this function is not dependent on S. What does it mean? You see how one can treat this function. This is the probability that our process starting from point X at time S turns out in the set gamma at the time S plus T. So if I have S plus T, S prime plus T, these probabilities are the same. Yes. If it does not depend on S, then this is in reality a function of 3 arguments. And I denote it by PTX gamma. If it does not depend on S, then this is a function of 3 arguments, Tx gamma. We will call such a process homogeneous in time. Okay? And let us consider example. Let us consider a Markov process for which X is a finite set. So suppose that cardinality of X is finite. So X that this is not does not concern this example. I will consider our approaches. In this example, our approaches in a space that consists of finite number of points. Okay, then and I will consider homogeneous. Homogeneous. So I have the approaches is determined by transition probability. I would like to write down P, T, X, Y, or T, X, X and Y, from Y, from X. Oh, I am sorry, I forgot to suppose that I always assume that sigma algebra B in X includes into itself all a single point sets. Such a set is measurable. Okay? So if I know the probability at points from X to any point, I can then calculate this probability with the sum P, T, X, Y. Okay? Now, let us consider this equality. That equality in our situation means that we have the number of checking equation means in our situation that PS plus T X Y equals the sum over Z from X P S X Z P T Z Y. It is not difficult to understand. And let us denote by P of T a matrix consisting of the elements P, T, X, Y. X is the number of row, and Y is the number of column. So this equality means that P of S plus T equals the product of matrices P of S, P of T. Okay.
Now the small p is because the third argument is
number.
I denote P P P T Y is P capital of T X a single point Z. Okay.
Would look at like 5 minutes. So let's consider this example to its end. Maybe we are over. I mean, like, let's finish with this example, and then we're
Okay.
over.
Okay.
Yeah.
Okay.
Thank you.
And what does it mean? This equation is for a well-known function, yes, exponential. But we have to assume the following addition, the following property. Our family of these functions such that this matrix tends to identity matrix as t goes to 0. Under this condition, it is not difficult to verify that P of t is e to the power t a, where a but a is a matrix with entries a x y, and those entries have the following property. These numbers are non-negative if x is different from y, and the sum over all y, a x y, equals 0. This is a consequence of the property that the sum over all y, p t x y equals 1. Again, okay? This is the derivative of t at the point t equals 0. Okay, so this is a consequence. So you see, all homogeneous Markov processes in a finite space, this space is called phase space in a finite phase space. All probability are of this form, where A is such a matrix. And I would like to formulate to conclude my lecture. Class today, I would like to formulate an exercise for you. Prove that if I take any matrix of some, right, and consider its exponent, this function, the power ta, I receive I obtain some matrix consisting of all non-negative entries satisfying this equality. You see, we have seen that if we have such process, then there exists such a matrix that P of T is complete form. On the contrary, if A is such a matrix, then E to the power Ta is a stochastic matrix. It means that its entries are non-negative and the sum over any row is equal to 1. Maybe next time I will explain how to prove that for any such a matrix, the elements of this matrix are non-negative. This is the main problem with this assumption. And I would like to show you how to explain, how to use the maximum principle for proving that the entries of this matrix using this. I explain how to prove that the entries of this matrix are non-negative. My time is over. Thank you.
Thank you for the very interesting lecture.